Okay, so Robert, I heard you have a nice sequence to tell us about, this comma sequence.
Yeah, the comma sequence was the sequence submitted to the OEAS 15 years ago or so, maybe a little bit longer, that recently came up again in a very nice paper. It's a sequence that's defined, it has something sort of a similar vibe to the Fibonacci numbers, where for the Fibonacci numbers, to compute more terms of the sequence, the next term depends on the previous two terms. But for the comma sequence, the next term depends on the previous term and the next term itself, kind of. Let me try and explain what I mean. So the comma sequence begins, it's here, it's this top row, 1, 12, 35, 94. The second line is not a part of the sequence, but it is crucial to the sequence. So what does the comma sequence do? What's its defining property? If you look at the commas, that's where all the action happens. So I look at a comma somewhere in the sequence, and what I do is I take the first digit on either side of the comma. So this comma is surrounded by 1 and 1. I write 1 and 1 down, and that gives me 11. And 11 happens to be the difference of these two terms. So 12 minus 1 is 11. And that's the defining property of the comma sequence. If you do this funny comma operation, like here, 12 and 35, you have 2, 3, gives you 23, and 35 minus 12 is 23.
Do you always have a unique choice of the next term?
Yeah, that's a good question. Let me show you how you would get the next term here. So we finished at 94, but that's not the last term in the sequence. So if we wanted to continue, we would need to put something here. How would we do that? So from the property that the comma sequence satisfies, there would need to be some number here. We call it a comma number. It would have 2 digits. The first digit would be a 4 from the comma rule. So that means that this is 40 something. Okay, so if you add 40 something to 90 something, you get 130 something or 140 something. But in any event, the first digit here is going to be a 1. It's going to be 100 and something. And that means that the comma digit, or the comma number here, then from the rule, has to be a 1. So 41. So that means that this is 135. That's the next term. So in this case, I think, yeah, we only had one choice. But sometimes when you're computing, you actually have more than one choice. So like I said, this was either 130 something or 140 something. In this case, our hand was kind of fixed. It had to be 130 something. But had there been a choice, the strict definition says you always take the smaller choice. So you always take the smallest number possible that you can write here. And that's the official definition.
In the first place, why do we begin by 1 and 12?
Yeah, 1 by 12. So 1 is another part of the strict definition. You just start off with 1, and then after that, 12 is actually determined from the rule. So if you want 1 here, what comes next? Well, you have a comma number down here. It's 2 digits. So we start off with 1. Something's got to go here. 1 plus something in the tens is either in the tens or in the 20s. So we should try and do the tens first, because that's what the rule says. Always try the smallest thing first. So it's going to be something in the tens. All right, our comma digit then this will be 11, so that gives us 12. So 12 is actually determined, although maybe we could have picked another number, but the definition says always pick the smallest one that you can.
If we continue further adding terms, then do we continue forever?
Yeah, exactly. That's the question, right? Because it's such a completely random definition. You know, you wouldn't expect us to do anything. So you go to 135. The next term, just reading up from the paper, is 186, 248, and you keep going. And what's really amazing about the sequence is it goes on for a very, very long time. It goes on for, in fact, 2 million terms. So after 2 million, let's see, 137,453 terms. After that many terms, you're always able to compute a successor. The sequence dies at the value 999,999,45. So 6 nines, and then 4 5. So that is the entirety of the comma sequence. It's a finite sequence. It goes for a long time and then dies.
After 2 million terms.
After 2 million terms, 2.1 million terms it survives, then dies.
How does this happen all of a sudden?
Yeah, that's a great question, because it actually happens all of a sudden. It took 2 million terms for it to happen, right? But it can happen all of a sudden. For example, so the original sequence goes for 2.1 million terms, but you can start off with things that die much faster. If you had started off with 3, you can check that the next number I think is 36, the comma number is 33, but then it's not possible to continue after 36. So if you start at 3, 36, you die immediately after 2 terms. So one of them lasted 2 million terms, and one of them lasts 2 terms.
Okay, how about other initial conditions? This is super weird.
Yeah, other initial conditions. So it's when the sequence was submitted, it's a big open question. If I pick different initial conditions, how long will the sequence last? One's 2 million, one's 2. What's going on here? So initially, we didn't even know if all the sequences were finite. Maybe there's some way that you could, sneak through all the bad cases where you might die and go on forever. But there was some kind of hand-wavy heuristic that estimated. The estimate is that the length should be something like 10 to the 100 over 12 on average. That's what we think that it should be. That's the average length. But this is only a heuristic. It's not actually a rigorous proof that they're all finite.
This is like the average length for different initial conditions? Or?
Yes. Yeah, that's the estimate, is that the average length for a different initial condition should be roughly that.
And how about 2? If you start with 2?
Yeah, that's a great question. What happens if we started with 2? Let's see. If we started off with 2, so the next thing, the comma digit, or the comma number will be 20 something. So this is either 20 something or 30 something. So let's see, we should try 20 something first. 22, and that gives us 24. So we get at least one term. Let's see, we can go again. Okay, so the comma number starts off with 4. This is either 60 something or 70 something. We try 60 something. That gives us a comma digit of 6 here. 46. That's bad. There's a carry. This becomes 70 something. So we can't do that. 60 something is out. Okay, so instead we try 70 something. Let's see, 47. And that's now fine. This gives us 70. What is it? 71? Is that right?
Right.
Yeah, 71. And I don't actually know how far this one goes out. But it goes for a while, doesn't it? It goes for at least 3 terms, which is somewhere between 2 and 2 million. So we're doing pretty good at bounding it.